lecture, part of the lecture, we're going to talk about stresses on an inclined plane, in particular for bars under axial loading. So, first day of class, we talked about how we had a bar, we can put it under axial loading, and we can calculate the axial normal stress. And the way we went about that is that we would take this bar and we would cut it to find the internal force that would keep it in equilibrium. And in this example, it's very easy. The internal force would be equal and opposite to P. And then we talked about how we can get the stress distribution, and we said that the axial normal stress would be the force in that bar divided by the area of the cross section. Now, at the time, we said that there are more than one way to cut the cross section, to cut the bar. We can cut it clean across the cross section, or we can cut it at an angle. So if we cut it at an angle, our picture is going to look a little different. Okay, here's my applied axial force. It could be tension or compression. And to keep this in equilibrium, we would have to have an equal and opposite axial force P. We're going to do something a little bit different now. Since we know about normal stresses and shearing stresses, we're going to take that force P and we're going to break it up into two components. One component being perpendicular to the area of the inclined plane, and one component being parallel to the inclined plane. So the perpendicular component, I'll call that the normal component, and the parallel component, I'll call that the shear component. So we have Fn and Fs. Let's see if I can sketch this in 3D to give you a better idea what the inclined plane would look like. Suppose we're looking at something like a 2x4 where we have a rectangular cross section. If I were to take the 2x4 and cut it at an angle, the slanted plane would have a larger cross-sectional area than the area of the cross-section. And we're going to go through the details on how to figure out the area of that if we know what the angle is. Right. So to stick with the notation that the book likes to use, they define this angle as the angle theta. Now, typically we would know some cross-section dimensions like the width and the height of the cross-section. If we want to find the stresses on the inclined plane, then it's pretty easy. Since stress is force divided by area, the normal force, or the sigma, on the inclined plane is going to be the normal stress, or the sigma on the inclined plane is going to be the normal force divided by the area of the inclined plane. And likewise, the shearing stress on the inclined plane is going to be equal to the shearing force divided by the area of the inclined plane. So really we need just two things in order to work all of this out. We need to figure out how to break the force up into components, and we need to figure out how to compute the area of the inclined plane. Let's do the area of the inclined plane first. That's very easy. Let's look at this picture. Here's the picture of the inclined plane. If I call this dimension L for the slant length, the area of the inclined plane is going to be equal to W times L. To find L, if I look at the cosine of that angle theta, cosine of that angle theta is going to be H divided by L. So that means that L will be equal to H divided by the cosine of theta. So if I know the cross-section dimensions, then the area of the inclined plane is going to be W times H divided by the cosine of theta. Now I'm going to give you a word of caution here. when I make up an exam or a quiz problem or whatever, I don't really pay attention to what the book calls the angle theta. I just give some angle. And it could be the angle that the book calls theta, or it could be the other angle in that right triangle. It works in a similar way. If you understand the geometry, then it works out just fine. So what I'm saying is, for example, if I give this as the angle alpha, well, then the sine of alpha is going to be h over L. So the area of the inclined plane can also be found by W times h divided by the sine of alpha. So these are equivalent expressions, and you can use either one. The point being, make sure you understand what you're doing and not just apply a blind formula. All right, so if we want the stresses on the inclined plane, we need to find the forces on the inclined plane in the area of the inclined plane. We've already done the area of the inclined plane, so let's take a little bit more closer look at the forces on the inclined plane. Let's start over on a clean sheet of paper, and I'm going to reproduce this force triangle. All right, so I cleaned a little bit of that up. The angle theta, as the book defines it, again, is the angle from the vertical to the slant. And I'm going to draw this picture a little bit larger. Our problem is we need to figure out which one of these two angles in this triangle is the angle theta. So let me draw this a little bit bigger. There's the force P. There's my Fn component of the force. And that adds vectorially to give me my force P. So this is the shear component. Now, if I reproduce this angle here, let me use a different color. If I draw this straight down, the slant angle here from the vertical is the angle theta. Now, it's kind of hard to see the way I drew it, but from this red line to the blue line is 90 degrees. So this angle is 90 degrees minus the angle theta. Well, that means that this angle in this picture is the angle theta, because from the blue dashed line to that slanted red line is also 90 degrees. Well, if that's the case, then the normal force is going to be equal to P cosine theta, and the shearing force is going to be equal to P sine theta. Now, I would encourage everyone to go through the trig and make sure you understand how to find those force components in terms of either the angle theta or the angle alpha, as I had defined on the previous page, which is this small angle right here. All right, so the stresses on the inclined plane then is the normal force divided by the area of the inclined plane. In terms of all these other symbols, it's the axial force times the cosine of the angle theta divided by the area of the inclined plane, which was W times H divided by the cosine of theta. The shearing stress on the inclined plane is the shear force divided by the area of the inclined plane, P sine theta divided by W times H divided by cosine of theta, or appropriate as the other with the other angle. And if you have the angles and the numbers for all these things, you can find the numbers for the normal stress and the shearing stress on the inclined plane. Now, at this point, that's all that you really need to understand very well. We need to do some work with these equations, though, and the book does this. And there's good things about this and there's bad things about this, but the book is going to take these equations and rearrange them a little bit more. So if we look at this sigma equation, we have P. If we flip the cosine theta up there, now we got a cosine squared theta, and we have a W times H. What is the area of the cross section? For the shearing stress, we'd have P sine theta cosine theta divided by the area of the cross section. Now we're getting into some very particular formulas now, and on an exam, The exam is not about how well you can remember formulas. You'll need to know some basic formulas, but the exam is always going to be about how well you can apply the basic concepts. So I don't want you to memorize very specific formulas. It's not worth it, and it's too easy to forget some of the details of those very complicated formulas. Instead, I want you to know what you're doing. But we need to talk about these specific formulas because we want to talk about some things that we can use these formulas with. Let's rewrite these one more time down here. Stress on the inclined plane. If we group this term, the force over the area of the cross-section, that's the axial stress. So sigma axial cosine squared theta. And the shearing stress on the inclined plane is sigma axial times the sine theta and the cosine of the angle theta. Now the reason why we want to get these formulas, and let me put in here, don't memorize these. The reason why we want to get those formulas is we want to do a little bit of work on them to find the maximum values. We want to maximize these functions. The reason why we want to talk about this is that some materials fail because of high normal stresses, and some materials fail because of high shearing stresses. Let's make a note of that. Your brittle materials tend to fail because of high normal stresses. And your ductile materials tend to fail due to high shearing stresses. So if we can figure out the angle at which we have a maximum shearing stress in a material or a maximum normal stress in a material, then we can predict how that material is going to fail if we know if it's ductile or brittle. All right. Let's take a look at, first of all, the maximum shearing stress. Many good engineering materials, many very useful engineering materials are made out of ductile materials. A lot of ductile steels, aluminum alloys, copper alloys, different metals are very ductile, and they fail because of high shearing stresses. All right, so let's maximize our shearing stress. So we just found out that the shearing stress on the inclined plane was sigma axial sine theta cosine theta. Now we're going to do a little bit of trig substitution here. We're going to note that sine theta cosine theta can be expressed as the sine of 2 theta divided by 2. It's going to help us a little bit. So now we can rewrite our shearing stress as sigma axial over 2 times the sine of 2 theta. If we want to maximize that shearing stress, we're going to take the derivative of that with respect to theta. Of course, sigma axial over 2, those are constants. Sine of 2 theta, if we take the derivative of that, we get 2 times the cosine of 2 theta. And we want to set that equal to 0 to get a maximum. And what we're going to do is we're going to solve for the angle at which the shearing stress is a maximum. Okay, since that's set equal to 0, those terms will go away. And we basically just are looking at cosine 2 theta for maximum shearing stress equal to 0. Now let's see. The sine of 0 is 0. The cosine of 0 is 1. Oops, the cosine, and if we want the cosine of 90 degrees, that'll get us equal to 0. So the cosine of 90 degrees is equal to 0. It's actually plus or minus 90 degrees. Now, 2 theta, then, is going to be equal to plus or minus 90 degrees. So that means that the angle theta at which maximum shearing stress occurs is plus or minus 45 degrees. So that means for our axial bar in tension, the angle where this is 45 degrees will give us the maximum shearing stress on that surface. We do also have some normal stress at 45 degrees. Of course, the normal stress on the inclined plane we found from that formula, we're going to use that, is sigma axial times the cosine squared of theta. Since theta in this case is at 45 degrees, cosine is 1 over the square root of 2, the cosine squared is 1/2. The normal stress on the inclined plane at 45 degrees is going to be the axial stress divided by 2. The shearing stress value on the inclined plane at 45 degrees, the formula is sine theta cosine theta. If we put in 45 degrees, since the sine of theta and the cosine theta are equal to 1 over the square root of 2, both of them, we also get the value of sigma axial divided by 2. So if my axial normal stress was 50 ksi, at 45 degrees, I have 25 ksi for shearing stress and 25 ksi for an axial stress. Now, we mentioned that ductile materials tend to fail because of high shearing stresses. Any other angle from 45 degrees, we do not get a maximum shearing stress. It's that 45-degree angle that gives us a maximum shearing stress. So if we can find a ductile material and do a tensile test on it, it ought to fail at an angle of 45 degrees. Let's see if I can get this set up and show you a picture of a tensile specimen that I took where it did fail at the 45-degree angle. I'm going to bring this window over here, and I'm going to scoot over to my document camera. What I have showing in this picture is a 0, 45, 90-degree drafting triangle, and here's a broken tensile specimen. This is an aluminum alloy. It's kind of an interesting project I had. We were testing some material that was going to be used as a meteorite debris shield for the International Space Station. This was a number of years ago before it was built. This is a very ductile aluminum, and I just taped the two ends together. And let's see if I can angle this. You can see the failure surface there in the image. But what I'm going to do is I'm going to align the bottom of my specimen with the bottom of the triangle, and we're going to see how close to 45 degrees that we can get with that failure surface. And look at that. That's worth zooming in on. I'll bring this down a little bit. See if I can get that to focus. Okay, make sure the bottom's lined up, and there it is. That's really, really close to a 45 degrees, and I'd say that's as exact to 45 degrees as you can get. So this was a ductile aluminum material. We pulled it in tension, and it failed right at that 45-degree angle, just as that theory has predicted. Okay, so what's our takeaway from all of this? The max shear stress for an axially loaded bar is 45 degrees to the axis of the specimen. That's one of those things that as an engineer that you ought to know. All right, let's take a look at the maximum sigmas on any plane in the material. Our formula for the inclined normal stress, inclined plane normal stress, is sigma axial times the cosine squared of theta. And if we want to maximize that, well, that's pretty easy. When theta is equal to 0 degrees, we get the maximum sigma. So if I have my bar, and this angle is 0 degrees, that means it would be maximum on the cross section. And it would be equal to our axial normal stress. Now at this angle, let's see if there's any shearing stress. Our formula for the shearing stress is sigma axial times the sine of theta and the cosine of theta. Of course, the sine of 0 is 0. We don't get any shearing stress. So that's kind of interesting. Where we have maximum shearing stress, we do get normal stress. Where we have maximum normal stress, we don't get any shearing stress. Now, if we were to plot these out, if you're using Craig 3rd edition, you can take a look at the book on page 66. But we can plot the variation of stress with the angle theta. Okay. If this is 0 degrees and let's say 45, 90, 135, and 180, the normal stress starts out as a maximum at 0 degrees, becomes 0 at 90 degrees, and it comes back up here to 180. And it's a very poor plot. It's supposed to be looking more like a sine. It's hard to draw on this tablet. It should look a little curvier like that, since they're sine wave functions and cosines that we're dealing with. The shearing stress plot as it changes with theta, it's a little bit different. It's actually 0 at 0 degrees. It's a peak at 45 degrees. Goes back to 0 at 90. Comes another maximum at 135, and then comes back up here. The place where they're equal turns out to be sigma axial divided by 2, and that happens at the 45 degree. And then down here at minus 45 degrees. My plot's not quite to scale. Like I said, it's kind of hard to draw on the piece of paper. All right, so if we go back and review, the most important thing I want you to get out of all of this is that one force can cause stresses in a bunch of different directions in a material. It can cause normal stresses, sigmas. It can cause shearing stresses, tau. We can find out what those stresses are by taking the force that acts on that plane in the material, dividing it by the area of that inclined plane. It's easy to find the area of the inclined plane if you know the dimensions of the specimen. Let me do one more example. And that's where I take a look at a bar that has a circular cross-section. Let's put some numbers on here. Say this is a 2-inch diameter, and we have 2,000 pounds applied in this direction, in the axial direction. And we want to find the stresses where that is a 30-degree angle. We want to find the normal stress and the shearing stress on that particular inclined plane. All right, so here's what we want to do. We want to draw a free body diagram. If we look at a side view, it'll look like this picture. The free body diagram needs to be in equilibrium. So we have those axial forces that are equal and opposite, and then we want to break that force up into its normal and shear components, and this being 30 degrees in this case. So the angle from the horizontal to the slant is 30 degrees. Well, that's really easy. The geometry on that is really easy. It's the same angle right here in this picture. So in this example, the normal force would be equal to 2,000 sine 30 degrees. And the shearing force is 2,000 cosine 30 degrees. Just breaking that force up into those components. Now to find the area of the inclined plane, this may look a little bit different because it's a circular cross-section, but we still need the slant length. I'll identify that as L in this picture, and what we know is the diameter. If I look at that picture, the sine of 30 degrees would be equal to D over L, so that means that the slant length is equal to D, in this case divided by the sine of 30 degrees. If we were to draw this in 3D, let's see if I can do that. The shape of the cross-section would actually be elliptical. Now the area of an ellipse is very similar to the area of a circle. Circle is just a special form of the ellipse. The area of a circle we've been using is pi over 4 d squared. The area of an ellipse is going to be pi over 4, the major diameter times the minor diameter. Okay, so that would be like our minor diameter, and that distance there would be our major diameter. The minor diameter is the diameter of the specimen. Minor diameter of the ellipse is just the diameter of the specimen. And the major diameter of that ellipse is what we just called L. Now since L is equal to D divided by the sine of 30 degrees, we get our formula that we had before. The area of the inclined plane is equal to the area of the cross-section divided by the sine of what I had called alpha previously, or if I use the other angle, we still get this formula back, area of the cross-section divided by the cosine of what the book calls theta. Okay, so there's another example, and then to find the normal stresses and shearing stresses on the inclined plane, the normal stress on the inclined plane would be Fn divided by the area of the inclined plane. In this case, 2,000 sine 30 degrees divided by pi over 4, 2 divided by the sine of 30 degrees. And the shearing stress on the inclined plane, the shear force divided by the area of the inclined plane. In this case, 2,000 cosine 30 degrees divided by pi over 4, 2 times 2 over sine of 30 degrees. Both of those would give us answers in PSI. All right, so take a look at a couple examples. Look at round bars, look at rectangular cross-section bars. Look at the angle alpha being given, look at the angle theta being given, and there won't be any problem that I could give you that you wouldn't have already worked.